Today we're going to talk about graphing radical functions. Well, really with this video we're going to specifically talk about how to graph square root functions. I went ahead and gave you a generic radical function equation though, just to remind that transformation rules do still work for this, same as the transformations that we've talked about in past lessons. You know, if you've got a number out in front of that radical as an a value, that can represent your vertical stretch or your vertical compression, depending on whether it's greater than 1 or if it's in between 0 and 1. If you've got a number being added or subtracted to x inside the radical, then that's your left and right movement, but it is the opposite of what you might think it would be, because a positive number actually moves it left and a negative number actually moves it right. And then if you've got any number being added or subtracted outside the radical, at the end of the problem, then you've got an up or down shift. But for today, what I really want to talk about is actually graphing these out. So let's start off simple. Let's say I just asked you to graph f of x equals the square root of x. Well, just like we graph with any other function, the best way to do that is with an xy table. Remember, with an xy table, you can pick any x values you want to plug into the equation. You plug those numbers in and you just see what you happen to get for a y value, and that's how you graph it out. Now obviously the nice thing with an xy table is, since we can pick any x value we want, if we're careful and we choose carefully, we can make this a pretty easy xy table for us. Especially with this function, it's important to be careful because we're square rooting. And we know that some numbers square root perfectly, but some do not, and so we want to be careful, we want to be picky with what we choose. First off, the question to ask is, what is the lowest, what is the least number that you could plug into that square root and get an answer from? Well, 0 is going to be the lowest number, the least number, because think about it. Any number less than 0 is going to be negative, and we know that if we square root a negative number, that becomes imaginary, and we're not graphing imaginary numbers on our real coordinate plane. We'd have to go to a complex plane to be able to do that, and that's not what we're talking about with this lesson. So basically, my graph is going to start at 0, because that's the lowest, that's the least number that I can plug in. So if I do plug in 0 for x, well, the square root of 0 is 0. So 0, 0 is a coordinate point. So that was important, because I want to know where the graph starts at. From that point on, we can kind of pick whatever numbers we want. For me, I'm going to say, okay, what's the next least number? What's the next lowest number that square roots perfectly, which would be 1. And then for my third number, I'm going to pick 4. I don't want to plug in 2 or 3. You can if you want to, but we know that 2 doesn't square root nicely, and neither does 3, and I don't really want to have to deal with nasty decimals. So that's going to be the 3 points I'm going to pick. If I plug in 1 for x, the square root of 1 is 1. If I plug in 4 for x, the square root of 4 is 2. And so what we see, if we go ahead and graph this out then, sorry, didn't mean to move it like that. Try that again. What we'll see if we graph this out is we put a dot here at 0, 0, put a dot at 1, 1, and then at 4, 2. And what we have is this line that curves both up and to the right, but mostly is curving to the right. Because if you think about it, after 4, the next number that square roots perfectly is 9, so 9, 3 would be a coordinate point, which means we're going to go 5 units to the right from 4 just to go up 1. And then after 9, the next number that square roots perfectly is 16, so now we're going to go 7 units further to the right just to go up 1. Right, we're consistently going further and further right just to go up a little bit. But we are still going to continue going up. It doesn't ever flatten out. It'll always continue going up a little bit at a time. But this is your parent function for a square root graph. So my recommendation would be, from this point forward, whenever you are asked to graph some other type of square root function, you basically have 2 options. You can graph it off the transformations, or you can graph it off an xy table. I prefer to always graph off an xy table. For example, let's say I gave you the function f of x equals 2 times the square root of x minus 5 minus 3. Let's say I gave you that. Now if we're thinking transformations, this is a vertical stretch of 2, a shift right of 5, and a shift down of 3. So you could just take this parent function off to the left here of the screen and just graph it based off those transformations. And if you can do that, if you can keep track of all those shifts, and especially if you can keep track of what that vertical stretch means in your head, then that's fine. Let's say, for argument's sake, that you're not comfortable graphing this off the transformations, and you would rather just graph it off an XY table. Here's how I'd recommend doing that, okay? If this is a square root function, as we just showed off the parent function, we know there's going to be a starting point, and then it's going to go off in some direction forever. Well, that starting point is always going to be wherever you get the square root of 0 at, right? Because whatever number, whatever x value you plug in to get the square root of 0, you're not going to be able to plug in any numbers less than that, or else you'll be giving yourself a negative square root, and we can't graph that like we talked about. So the first thing I want to determine with my XY table is what x value is going to cause this graph, this function, to get the square root of 0. Which means I don't need to look at the 2 or the negative 3, I'm really just looking at the x minus 5 inside the radical. Well, if x is being taken minus 5, then if I plug in positive 5 for x, 5 minus 5 would give me 0. Right? Meaning, if I want to plug 5 in, I've got 2 square root of 5 minus 5 minus 3, which gives me 2 square root of 0. The square root of 0 is 0. 2 times 0 is 0. And so it looks like if I plug in 5, I get negative 3 as my y value. That's going to be our starting point for our graph. So that's a very important point. Now recognize you could have also found that point from the transformations, because from our transformations we knew it had a shift to the right 5 and a shift down 3. Well, if from 0, 0, which is where our parent function started at, if we shift 5 units to the right from 0 and 3 units down, that would be the point 5, negative 3. So you could have got that point either way. But that's how I'd be thinking of it if you want to graph by an XY table. And so with the XY table, I need 2 more points at least, because you always want to graph at least 3 points to make sure you know the shape. Because if you just get 2 points, you can make any graph seem like it's a straight line. We need at least 3 points to be able to see any curves that are going on, which we know is going to happen here based off the parent. So again, when I'm choosing x values, I want to make sure I'm carefully choosing ones that give me nice numbers that square root perfectly. Well, we already discussed that 1 square roots perfectly. So the question is, what minus 5 would give me 1? Well, 6 minus 5 would give me 1, so 6 would be a good x value to plug in. If I do that, if I plug 6 in, that means I've got 2 times the square root of 6 minus 5 minus 3. 6 minus 5 is 1, and like we just said, the square root of 1 is 1. So then, 2 times 1 is 2, and 2 minus 3 would give us negative 1. So there's another point. And then finally, I need one more point. I've already used the square root of 0 and the square root of 1, so in my opinion, the next easiest number that square roots perfectly would be 4. So what minus 5 gives me 4 in that square root? Well, that would be 9. If I plug 9 in, that means I've got 2 times the square root of 9 minus 5 minus 3. 9 minus 5, sorry, that's a really bad 5. 9 minus 5 is 4. The square root of 4 is 2. 2 times 2 is 4. And 4 minus 3 would give me positive 1. So now I can graph this function out try and hit that on a line better. That's better. So 5, negative 3 would be right here. 6, negative 1 be right here. 7, 8, 9, and up 1 would be right here. And so remember 5, negative 3 was our starting point. And so we're curving off to the right and up forever. And you can see, if you look at these two graphs, what that vertical stretch did. Because it's certainly going more up. Certainly, it's a more gradual curve with that stretch than it was the way it was normally. And you could have figured that out because notice that our y values changed by 1 here, whereas our y values here changed by 2. Right, so there are things you could have done just to graph it off transformations. I don't want to act like you can't graph it off transformations. But if the transformations are something you're not super comfortable with, then just do it off an xy table, and you always want to try and get the square root of 0, the square root of 1, and the square root of 4, because those are going to give you the easiest time. That would be my recommendation. Last thing I want to talk about for this lesson is domain and range. We have discussed domain and range in previous lessons, but remember, domain is the x values, range is the y values, meaning the x-axis goes left to right, so when I ask you for the domain, I'm basically asking you how far left does the graph go, how far right does the graph go. And so looking at this graph, the leftmost point is right here, and then we can see that it goes off to the right forever. So if I want to do my domain then, I'd start with the left side, the lesser side, and so the leftmost point is 5, right? This point right here is 5, negative 3. If domain is the x values, I should be using the x value from the coordinate. That is a closed dot, so it should be a bracket. Remember, we've talked about the difference between bracket and parentheses for interval notation. If the graph is going off to the right forever, which we can see by this arrow, then the math term for forever would be infinity, this little sideways 8 symbol. And that infinity is both positive, because it's going right, the positive direction, and we're going to use a parentheses because brackets are for closed dots for specific points, and infinity is not a point on the graph, infinity is more of a concept, so it's always going to need to be a parentheses. Then if we want to talk about range, range is the y values, meaning we're looking to see the up and down movement. We always want to go from least to greatest, so we want to know how low the graph goes first and how high the graph goes second. Well, the lowest point would be the same as our leftmost point, this 5, negative 3. But since it's range, the y values, we want to use the y coordinate of negative 3. It would still be a bracket because that is still a closed dot. The highest point of this graph, well, while it's mostly going right, remember we talked about while it's mostly going right, it is going to continue going up a little bit forever. And so since it's going up a little bit and up a little bit more each time we get a new point, we would say it's going up forever towards positive infinity again. Recognize for domain, positive infinity is going to the right forever. For range, positive infinity is going up forever. But in interval notation, they look similar. So that would be your domain and range. And yeah. And that would be how to graph square root functions.